properly. So there is your voice is just a little kind of weakening. I don't know why. It's
Is
okay.
it audible now, ma'am? I was
It's
little away from
audible,
the
sir,
speaker, I
but
think.
maybe there is an issue with my laptop,
Okay,
probably.
okay.
Yes, so
No.
no issue. So thank you so much, sir, for inviting me for this AP Andhra Pradesh SCHE program. And as sir just told, he believed on me for just a long many years, and I will try my level best. So basically, as said, just have said, I have very minimum experience in terms of number of years, but whatever experience I have, that is primarily on quantum. But though I have recently a few time, like for a few like 1 or 2 year experience, you can say, on generative AI as well as blockchain. So I'm working on that. I'm literally learning for the sake of industry purposes only. So I'm just learning those things. But quantum is kind of something which I have started from 2014. So my BTech project was on binary welded tree, and followed by my MTech project. It was also on quantum. Then my PhD that I'm continuing. Meanwhile, I joined one like a startup kind of thing, you can say, but it was actually the mother company was a Israeli gambling company. So I worked for that as well. It was for a quantum cryptography stuff, and we developed me and a few of my members. Um, we developed a QRNG, and that was actually confirmed and acknowledged by Professor Adi Shamir, which is the S of RSA. So I actually take it a lot because we presented this idea to in front of him, and we presented that why RSA is in threat. So you can understand that RSA was invented by him. He was one of the core inventors for RSA, and we are actually telling that quantum computers, for these reasons, they actually can put threats to your invented algorithm, which is primarily the base or backbone of any of the cryptographic application. So that was something which I personally acknowledge a lot. And after that, I joined. I was doing my GRF. I cracked NET GRF with 100 percentile for computer science, and post that I was doing it. Meanwhile, actually PwC called me that we need some member for quantum. Our team is very less, so like size is very less. So we want you to join. So post that, I actually left my core research kind of passion, and then I joined PwC. And thereafter I learned a lot of like industry academia collaboration, a lot of like what I need for what is the GTM and how fast you should work on. uh, it cannot be, because initially I started working on quantum natural language processing in PwC. I started with that because it was very niche. So suddenly they stopped it, and they told that okay, you have to explore those ideas that is very like low hanging fruit that can actually bring. So for quantum, it's so niche, it's so like hardware dependent. So ideating something for these kind of technologies like Gen AI or quantum is very challenging. So fortunately, I got that opportunity in PwC to work on that or to face that challenge. And also, like after that I realized that okay, that these kind of research is not only the something that I can pursue. So I took up another challenge. Well, I'm a mother of like two children, and one is 3.5 and one is 1.5, and still I dare to take up a challenge that okay, let me pursue that 1 year LDP, long duration program from IIM Calcutta. So I joined for that as well, just to learn that the business management tricks, the tips, or how we can translate a niche technology to the management, or what are the business aspects that we can have, or we have to every time keep in mind. What is storytelling? How we have to like convince our stakeholders, or kind of say kind of our clients, whatever you say. So that is kind of an idea. So when I actually met professionally Dr. Pilli in 2021, I lacked this kind of expertise. I was a core research person who were having some idea on the researchers, only on the research part, and a few of the academics computer science part. So right now we can say that you will be finding maybe a bit of a mixture of everything, because whatever we study right now, so we are trained in a way that we have to think that how we can commercialize it, and this is very important. So on that note, and this is a brief of whatever I have done or I have till date explored. So on that note, I will be happily want to start with the quantum computing from my light. So whatever I will start with, maybe it will be a part of, let me just share my screen first. So it will be a part of my exposure to both the academia as well as industry. So it will be a blend of both. I hope it is okay now. Yeah, sure. So yes, so
Yes, ma'am. You can make it full screen. Yeah. Yes, ma'am.
yes,
We will
yes.
see.
Okay, okay, sir. So on that note, let me start. So right now I'm pursuing both the things. I'm working on CTIO. I have not updated it in PwC US Innovation Hub. That is a commercial technology and innovation center, as well as the I'm a like part-time research scholar from University of Calcutta as well, under Professor Ramnan Chakraborty. I'm doing research under him. So here is where I want to start. So, I guess yesterday also you had a few knowledge on what is quantum computing and all those stuff. So I'll not put a lot of time over for that. But again, so quantum is not really something that can be covered in 2 hour session. So considering that, so actually the thought is now we have to focus more. So the thought is, why do we need quantum? What was that criteria that enabled us to research or to do that these FDP on quantum? So the idea is that first of all, there is a lot of industry traction here, because all the core giants suddenly, for some reasons, we will explore that they have put their money in this technology. Now the thing is that why they have put this. Okay, so the answer is, that with the evolution of computer technology, there were a lot of things were there, like first generation, second generation, third generation, fourth generation. Right now, we are standing somewhere in between the HPC, high performance computing, big data, everything we are doing. Now, the thing is that there are a certain kind of challenge with respect to the speed up that we can achieve. Okay, and the whatever we can do, pardon my voice, it's broken already. So but whatever we can do, it is really based on the classical physics, based on the TTL logic, transistor logic, and all those stuff, that NP and PN diode. But the thing is, suddenly there are two different type of computing approach that were there theoretically. Suddenly there is a breakthrough in that. What was those two technology? They were DNA computing and quantum computing. What is that? What is the key point for that? Both of these technologies were a little different than the classical physics or how it operates. So in terms of that, like DNA computing relies on our own DNA system, how it works, how the nucleotides and the nitrogen bases they paired up, like AT and GC, or for RNA it's like uracil. So all these things, and if you change any combination, which is called mutation, that will create a whole different community, right? So that kind of an idea. And I don't know if you know or not, but the monkey and human being, the homo sapiens sapiens, we differ only by maximum 2 to 2.5%. Rest of everything that we share, or our thought process, our genetic structure, our genomes, everything is same. So right now you can understand that how precise or how powerful these 2% is. So similarly, just like the DNA, there is another concept, there is another phenomena, or some say particle existing in nature, which is called light. Now, what light possesses is it has the property to exist both as a light form as well as the wave form. So, it can exist in both forms. Now, what is the power of it? Say light form, which we believe that light exists in only the particle form, okay, not the wave form. Particle means it is very discrete, So whenever we say particle, it means either a zero or a one. But whenever we allow it or we can perceive it as a wave, you can imagine that it is a combination of possibilities. A wave is a continuous signal. So at one point, maybe you have a certain possibility, then second point a different one, third point a different one, what? But altogether, if you can exist as a wave, definitely that means that you can exist in multiple possibilities, and most importantly simultaneously. The simultaneous existence of this property of light enabled us to thought more on the quantum properties of light. Quantum is nothing but the quanta or the packets of energy. So right now we want to move on to quantum physics instead of relying only on the classical physics. Have you got that? So that was the motivation that we want. We actually want to invent some new technology. It is not that we can increase the size of RAM or we can increase the size of, say, CPU power. We can power it up, or we can use some more data warehouse to store more data, to mine more data. That was not the thing. Right now we are focusing on completely shifting to a new, different or new genre of technology, which was DNA computing and quantum computing. But later, because of certain reasons, DNA computing couldn't do a much, because we couldn't do a lot of invention there. Even in 2013 or 14, there was a lot of such hype words around DNA computing, but post that it gradually got diminished, and the one catch or the one keyword that kept on increasing is quantum. But the thing is that we need to know that quantum physics is something that already exists in nature. But what we are more interested about is to know that what quantum or how we can leverage the power of quantum physics. So fundamentally, I want to clear this concept that quantum physics or all the quantum mechanical phenomena, they already existed. Now, in the recent years, say 10 years or 15 years, okay, what we are focusing on, and primarily when in 2026 IBM for the very first time introduced the Qiskit platform, the plug and play, all those stuff with the quantum gates and all. So from that onwards, we focused on that how we can leverage quantum physics in order to solve some real mathematical problems. So that particular field of study is known as quantum computing. So there is a difference between quantum physics or quantum mechanics, which you can equivalently like toggle between, and what is quantum computing. There is a difference, right? So quantum computing is primarily that field of study that relies on quantum physics in order to solve certain problems, not all. Okay. Now, focus on that. It can solve only a certain problems, not all. If you are having any question, you can put it on chat. I think I can see that and I'll be answering that. No issue. Meanwhile, if you want to me to pause, you can directly put it on chat. I can see that, then I can pause there. I will answer be I'll be answering your questions. Now, next is Moore's law. The same concept. So Moore's law says that the amount of information that you can store on a given amount of silicon has roughly doubled every 18 months. Now you can imagine that how much data sensitive we are. Even the fourth world war or the third world war, whatever we can see, or the next gen any world war, is thought of to be carried out only based on or only for the information. So information is the next generation key. It is the key that we want to protect, or that we want to actually manipulate. Anything you say. So information is the most important factor. Now, that information that we want to store, that is also getting doubled every 18 months, right? That is 1.5 years. So there is a huge increase in demand of the information that you want to store, and only by storing some information we cannot do anything. So we have to manipulate, or we have to do a further processing with with that available information, though that is also a challenge. So we needed something. So this is another arch that the technology is also right now actually putting up his hands and telling that, okay, so we are also going to saturate. And the solution only cannot be like more in by cannot be like increase the number of CPUs and then only you can increase the computing power, because it's that is so compute heavy or so costly that you cannot avail that. So you needed a solution that if nature by default allows us something to do with only one CPU, you don't need multiple CPUs, but it is able to solve more number of data or more number of problems together. That is something that we are aiming, and this is the difference between parallel computing and quantum computing. So in quantum computing, it offers a lot of speed up, a lot of data it can handle together. Parallel computers also can handle a lot of data, but the thing is that difference is for parallel computing, we need to employ a parallel algorithm which will work in between multiple CPUs, and also some communication layer needs to be there, some overhead will be there, latency will be there, a lot of stuff will be there, and most importantly multiple CPU need to be employed. Whereas in quantum, in order to get the same thing, just like four CPUs, we just need one quantum computer of 2 qubit. So it's one QPU, quantum processing unit, that can actually serve the service of multiple classical HPU or high performance computing units. Right? Pause me, please pause me if you find anywhere that I should be repeating or you want me to repeat, please pause. So next is, I just want to story tell to you in the first class of mine, nothing else. I just I want all of you to be in sync with what we are going to learn or what we are going to solve or what we are going to see next classes. I just want to give you a glimpse of everything around quantum. That is my target for today. So next is, what is an algorithm? If you are from computer science, if you are from mathematics, if you're from electronics, you should be knowing it. It's a very generic term. So what is an algorithm? Algorithm means there is some recipe, in very easy words. जैसे cooking recipe होता है, that is an algorithm. So that means there has to be some raw material, that is the input, and it should be able to give you some output, at least one output. And often, even if there is no input, your recipe can produce some output. So that means an algorithm is a process that will lead you, or that is a kind of a function or a mapping that leads you in between an input and an output, where number of inputs can be greater or equal to zero. Even for no input, it will work for few algorithms, not all, and number of outputs will be greater equals to 1. That is at least one output you have to generate, right? Now, the next question is, okay, we got that, what is an algorithm? Now the next question is, what type of algorithms are there? How many different types of algorithm can be there? That depends on how the algorithm is producing the output. If it is producing the output in terms of an yes or a no, then you call that problem which that algorithm is solving as a decision problem. That is, whether it halts after these say 10 steps or not. So I will be just counting 10 steps. If it is done, I will say it's yes. The Turing machine will say yes, otherwise it will say no. But if my algorithm takes say something which cannot be said or cannot be given an answer like an yes or a no, or it is something kind of an approximation or something in between, then we call that kind of problem as an optimization problem. So by the term optimization, you can understand that it has to be a little difficult. It's not really that easy binary search where we are given that number 5 and we have a 10 size array and we have to say that okay, whether 5 is present or not. So by only by answering that, you cannot get rid of in case of the optimization problems. You have to actually solve something and find what is the optimal value for that. For example, the knapsack problem, which is the fractional knapsack problem, say, which is solved using greedy technique. So we take it, we choose some fractions, and accordingly we decide that what is the optimal cost, whether we have to go by profit or we have to go by weight. There is a minimum weight first we have to pick up, or it will be a profit by weight. That ratio we will be taking, and wherever it is maximum, that is with the minimum weight we can grab the maximum profit, we will be choosing that. So likewise, based on some goal or optimization goal, whenever we proceed, that is called an optimization problem. So in an optimization problem, our every time our target is to get up or come up with the best available solution. If it is cost, our target is to find the minimal solution. If it is time, our target is to find the minimal solution. If it is efficiency, our target is to find the maximum solution. If it is profit, our target is to find the maximal solution. Why I am calling maximal? Because maybe for that particular problem instance there can be multiple solutions that lead to the same value, same optimal value. So in that case, we will call both the solutions as maximal. But if it is only one, okay, then we will call it maximum. That is the logic. But the challenge is these kind of problems, which are kind of like optimization problems, they are actually at times can be very hard, very hard. So just for a like say example, say for example you are a salesman, you have given 10 different cities to travel, and the condition is you can only travel each city exactly once, and post that you have to come back to the original city, and no city you can repeat, and absolutely you have to come back to the original one without repeating any city. You know in what, in mathematics what we call this one, this particular kind of data structure, what we call it? If anyone can put it in chat, I'll wait for 30 seconds or say 10 seconds. Any one of you know that what we call this thing? Say I have to traverse 10 cities exactly once, no repetition, then I have to come back to the original city. You know what kind of data structure I am talking about? If any one of you know, please put it on chat. Or if you're allowed, you can also like speak up, no issue.
They have put on chat one.
Okay, let me check what you have said. It is taking time. uh no, no. Traveling salesman problem is a problem. What I'm asking is what is the mathematical like data structure, what is the, in terms of maths, in terms of graph theory, what we call that kind of graph? No, it is not permutations. TSP is the name of the problem. I got it. But I asked that what is the data structure? No, it is not path. What path? Derivative is nothing. Digraph is a directed graph. Simon, no, it is not that. Consider the tool, consider the path. What kind of path it is, or what kind of cycle it is. There is a particular name. It's very, very famous. You should be knowing that. Yes. So Shobha Bindu. Yes, yes. No, no, no. I got my answer. No, it is not MST. It is not minimum spanning tree. It's completely different. MST is something that dreams are cruscals they solve. It is completely different. It is let me go back. It is basically that one, that Hamiltonian cycle that I was talking about. So it is a Ham cycle or Hamiltonian cycle. It is very important one, and our target is we call it a Ham cycle where exactly, even if you want you can skip some edges, but definitely you have to cover each vertices exactly once, and you have to come back to the original one. And this particular mathematical structure or Hamiltonian cycle, which is we use in TSP or traveling salesman problem, is very very much useful, and it is a very important use case as well for our quantum computing. So it is something that is used for, say, supply chain management. It is used in route optimization. It is used in logistics. So there are a lot of applications of this particular TSP. So just brush it up, okay? Whatever you have, about TSP or dynamic programming, just brush it up. It is very very useful. Okay. Now the question is that why we are talking about that. Now, just to tell you, if you do not know, that the time complexity or the space complexity of traveling salesman problem, the space is n into 2 to the power n, and the time complexity is n square into 2 to the power n. Now, if you put a value of n equals to 5, it will be how much? 5 square into 32, that is 25 into 32. Now if you put n equals to 15, how much it will be? Or say 60, it will be 2 to the power 16, which is 655 something, into 16 square. You can imagine that how it can increase. Or even if it is n equals to 10, it is 1024 into 100. So from 25 into 16, or 25 into, say, 25 was for 32. 25 into 32, it got 1024 into 100. So that is kind of some expansion or exponential factor that you can see. So that is why, in order to solve these kind of real problems in real time, we actually needed some better solution. And these kind of problems are called NP hard problems. Why it's called NP hard? Tomorrow, if possible, I'll be giving you the mathematical description of NP hard and NP complete as well. So it is basically something that, where we believe that there is no problem in NP which is as hard as this particular problem. That means if I can solve one problem, at least one problem in this particular set of NP hard, I can actually solve any problem, or any problem that belong to NP. And what is NP complete? Almost same, a bit confusing, but the only thing is that here NP complete problem means we have to pick up one problem which already exists in NP, then we have to solve it. And if we can solve it, we can claim that all problems in that NP set can be solved. That is the difference. But the real thing is, for this NP hard or NP complete problem, quantum or say classical computers, they really lag behind. They are not that efficient. So even if you apply, say for TSP, if you apply some greedy technique, maybe it can be solved for n square, but there are a lot of approximations here. We can never get that like optimal solution. And in order to get the exact solution, you need to actually put the n square into 2 to the power n. You know that where n is in exponent, it is exponential. We want to get rid of that. Assuming that you are from computer science or electronics or electrical or mathematics, you must be having this idea that if anything x to the power n or n to the power n or k to the power n is given, or 2 to the power n, 3 to the power, anything where n is in power, that means it is exponential. We want to get rid of it. So for these kind of problems, we actually should target quantum computers to solve it. They can come into play, right? Now, complexity classes, as I have just said, that there are primarily four classes that we should be knowing, that P, NP, NP complete, NP hard. I guess you will also be having more exposure on the complexity classes. Just to give you the full form of it so that you have a better understanding, P is the polynomially solvable problem, which can be solved in a deterministic polynomial computed machine. NP is something, it is not non-polynomial, it is non-deterministic polynomial where a problem can be solved by a non-deterministic computer in polynomial time, which of course we don't have, or it can be solved in non-polynomial or exponential time by a deterministic computer, which we all have. That is why we call it non-polynomial. It is just because that we have only non, like non, sorry, not non. We only have deterministic machine. But what is a non-deterministic machine that we can have? A quantum machine, right? It is non-deterministic because it is in wave. So I don't know where I want to be like. So it's kind of a multiple possibilities together. And what is NP hard? I just have said what is NP complete. So NP hard means it is as hard as any problem that reside in NP. NP complete means it already is in NP, but it is very hard. And if we can solve one problem for NP complete, then definitely all problems that is there in NP hard set that can be solved. And we will actually mark them and we call that P equals to NP equals to NPC. So that will solve our Cook's theorem in automata. So are you understanding? These are the real issues for which quantum got evolved. ऐसे ही कुछ नहीं है कि just we came up with something, it's just a niche technology without any base or without any ground. These are all the fundamental grounds that motivated this new technology to evolve. And I hope that exactly the same thing is there for blockchain as well as any of the niche technologies. So these are the motivation. Now is the example of factoring. Now we are into like, let us take a one real problem, say factoring. What it is, I will be giving you a number 60. I will be asking you what are the factors of it, and just take a pair like say 12 and 5. That constitutes to 60, or say 15 4, they also 320, it also is 60, 10 6, it is also 60, assuming the vice versa, it's symmetric, assuming that. So all of these numbers are factors of 60. But if I give you, or if I ask you, okay, say if I give you 12 and 5 and I ask you, please multiply them and tell me what is the answer. You will be answering it quickly that it is 12 into 5. If it is 1200 683 multiplied by 25,897, then also you can solve it very quickly using some Python code or some your calculator. But the thing is that if I ask you, if I give you that say 10 digit long decimal number, and if I tell you that what are the factors of, are you assuming that that is very difficult? Even if you find the factors, if I say that what are two factors that I actually have chosen, that can be very difficult. Pardon? So similarly, like just like the factorization problem, the same idea was taken by the RSA, Shami, Rivest, and Adelman. And this is very fundamental problem of quantum cryptography. This RSA. The asymmetric one. If we discuss that in quantum communication, maybe we will be discussing about a lot more about this. But this is very fundamental, and in a lot of security applications like your email, say SMTP, HTTP, TLS, like transport layer security, in a lot of such real things that you use every day, they actually rely on this particular algorithm, which is a cryptographic algorithm for encryption and decryption. But the key or the fundamental maths behind this is this basic factoring. So they have done a very simple thing. कि let us choose two very large prime number, तो उसको multiply करके दे देंगे, और we will be taking one of their factors as a private key public key pair. Now an eaves or say eavesdropper or intruder, if they have to predict that what is the correct factor, they have to do all the brute force. But brute force is going to take a lot of time. How much time? You can see that in order to factor, definitely we have to choose a very large number, of course that. So, but in order to factor a 300 digit number, you can see that the best algorithm, if that is the best algorithm, like means we are not using say greedy, we are using dynamic programming or say some amortized algorithm which are already very much proven to be the best one. Lower bounded theory, everything we have satisfied. That is going to take on a terahertz capacity classical computer, right? That is 10 to the power 12. cycles per second. On that particular type of computer, the best algorithm ever known, if it is classical, it is going to take 10 to the power 24 number of steps and 1,50,000 number of years, which is of course not practically feasible. Okay, so when they have seen that, when they found that, they relied on this one. They thought that okay, factoring se kam chal jayega, we don't have to do anything else, because the difficulty of factoring, just focus on the last two, like the last minus 1 point. The difficulty of factoring is the basis of security for the RS encryption scheme, because in order to factor the very large number, which is the product of again very large two large prime numbers, is going to be so difficult that an eavesdropper cannot really crack it in real time in his lifetime. That was the idea. So information security of interest to private and public sectors, all of them relied on this particular technology called RSA. Now challenge क्या है? Challenge है quantum. Again, another motivation. What is quantum? So we वाला quantum computer which is inspired by and taken by or say prepared by or using quantum physics postulates. They are so powerful. How they are powerful, we have not yet learned. But they are so powerful that whatever a HPC or high performance computer with a gigahertz capacity, that is 10 to the power 9, mega is 10 to the power 6, or giga is 10 to the power 9, is going to take 317 trillion number of years. Trillion means 317 into 10 to the power 12 number of years to break only a 2048 bit RSA key. Where let me tell you, I'll be talking about this a lot in the quantum communication. But 2048 does not mean this is the key size that you can actually use. Just like the bandwidth and throughput, there is a lot of difference. Say RSA 2048 may be practically offering only 80 or 90 key bits that you can practically use. Rest you cannot use. So just like the bandwidth and throughput, here also there is a huge difference. So with that note, even after that complexity, so that is going to take 370 trillion years. So now you can understand that we don't have to worry about it. It's so huge. No one can really break us. That is why JP Morgan, all these banks, all these sectors, finance, defense, everywhere, you can see primarily the algorithm that is under use is RS. Now, just focus on the last line. On the other hand, a quantum computer of only megahertz capacity, that is, if a quantum computer can process some task in 10 to the power 6 cycles per second, only with that speed, then that quantum computer can do exactly the same cracking or key cracking in 10 seconds. Now, whenever this particular thing got published, then NIST, National Institute of Standard and Testing, in collaboration with US government, in also the European Union government, they actually focused a lot on that what our private data, like it is going to be tracked, and that attack is called harvest now decrypt later. You can imagine that what it is. Like right now you might not be having say a very powerful mobile, but you can actually take some a few members numbers and store it somewhere in a logbook. Now you are like, whenever I'll be giving or I will be assigned to more power, I'll be using that power, computing power, in order to break all of their numbers so that I can directly get into their bank account details and all the stuff. So similarly, the same concept is here, which is called harvest now, HN, decrypt later, DL, HNDL attack. अभी स्टोर करके रखते हैं. Whenever we got time, whenever there is a very powerful quantum computer available, commercially available, we'll be using that and we'll break that. This is another motivation, that is quantum threat is another motivation for quantum computers to evolve. Why? We will see that. Because we want to have certain solutions, problems we are all talking about. What is the solution? So then for this particular thread, we actually have to thought of some different genre of, say, key exchange or cryptographic algorithm, so that our very well known RSA we no need to use further, and we actually can rely on some better versions than RSA. So these are the real motivations for which we are learning quantum and quantum cryptography communication, all these things. So classical computer, they have the power to store everything in terms of an n bit, but quantum, they can do it in 2 to the power n. A very good example or very old example that I provide here is, say you have 5 fingers in your hand. So if I just give you, say, uh, I tell you that okay, finger down is 0 and finger up is 1, and you have to store, say your 1, 2, 3, 4, 5. Let me go. So finger 1, 2 are down, and 4 is down. Then what is the information that you are storing? 1, 2, and 4 is down. So definitely it's 0, 0, 1, 0, 1. For classical, very easy. Or finger down is 0, finger up is 1. But if I tell you that your finger need not to be in up or down, they can be anywhere in between, which I do not know. And you have to store 0, 0, 1, 0, 1. Or say, how many numbers, if I ask you that how many numbers you can store with your 5 fingers, if you do not have that pressure to be in either up or down state, then you can be in anywhere between up and down. Now if I ask you, it can be either a 0 or a 1 for the finger 1, and considering that finger 1 can be either 0 or 1, your finger 2 can be also either 0 or 1, and your finger 3 can be either 0 or 1. Similarly, all 5 fingers. So what is the total combination? It is 0 or 1 into 0 or 1 into 0 or 1 into 0 or 1 into 0 or 1. So in total, you have 2 to the power 5. Why 2? Because 0 or 1. Now why 5? Because you only have the provision to use only 5 fingers. So it is 2 to the power 5. That is 32 different numbers you can actually store using only your 5 fingers. Now say finger is quantum bits or qubits. And if you have, say, 5 qubits, you can store what? You can store from 0, 0, 0, 0, 0, which is a decimal 0, to 1, 1, 1, 1, 1, which is a decimal 31. That is 0 to 31. All the 32 numbers you can actually store using only 5 fingers, equivalently qubits. Are you getting the point? So now again, स्टोर करके तो रखेंगे नहीं, स्टोर करने के बाद कुछ तो करना है. What power you are getting after storing it? You are getting the power of manipulating or experimenting or actually calculating using the help of all those 32 information. Now say for example 32 are, say, not number, it is just like that, say it is a add function. So add, say, xy. Now you can imagine what is the power. Say you are using a quantum computer in order to, in the very first step of your detailed computation. Again, there is no particular kind of need that every time you need to use a quantum computer. You, of course, you have to think of some hybrid one. But say in the very first step, where just you have to multiply two, you have employed a quantum computer, and that is very, very huge, millions, trillions of data there, which you are just adding and storing. And then one algorithm you are using, which is basically maybe classical or quantum, depending on your feasibility, cost, supplied, everything. You are actually calculating what is the minimum one. Say your logic is this much. You have to calculate you have to add two numbers, pairs of numbers. Post that, you have to just do the minimality checking, where what is the minimal number of the summed value you have to calculate. So for that, now can you imagine that all those summations, if you give the provision of those many fingers or qubits, all those provisions can be done in a single query, only one query, like SQL query. You don't have to really, there is no for loop, nothing. So for all those combinations, there is no one into those many number of queries. Rather, it's only one query, which is a quantum query to a quantum computer. Post that, you just need to check the minimality. If you can do that in one query again through some smart algorithm, then it will be only 1 plus 1 equals to 2 number of quantum queries. Are you getting it? So that is some sort of exponential power that we actually get from quantum computers. So on contrary, whereas in classical, with 5 classical bits or register of size 5, we can only store one one 5-bit information, only one. What is that one information? 00101. On the contrary, on quantum, with 5 qubit quantum register, what we can store 32 values. Whereas on contrary, on classical, we can only proceed with one input. Thymine 80 pair GC pair. I don't know that whether after 80 it will be TA or GC or CG. I don't know that. It's very non-deterministic, but based on whatever I have, accordingly we are going to get the output. Similarly, like quantum. So this is the power. But there are a lot of stuffs that every power comes with responsibilities. Similarly, here also, you are getting you can leverage the power, but how you will be manipulating with the power is something that we are going to learn in quantum algorithms, where we will be learning that how through very prescriptive analytics actually we can do, or say measurement, very smart measurement, or as per our demand, tuning that measurement. With all of these things we can do with a quantum computer. Okay, because even if you want to say store 17 units, 17 number of inputs, you need how many qubits? 5 qubits. Why? Because 4 qubits can only store till 16. 5 qubits only can store 32 or more than greater than 16 and less than equals to 32. But in order to store 17 unit information, you need a 5 qubit quantum computer, which is again very challenging. Everything is in superposition, everything is tied up. Now we have to actually filter out all those remaining 15 combinations. Why? Because you only needed 17 units, but you have employed 5 qubits. So that again is a challenge. 2 to the power 5 is 32, 2 to the power 4 is 16. You needed 17, so you have actually accidentally employed one more qubit. So how to handle those qubits? How to do or how to leverage other quantum phenomena like interference, constructive or destructive based on our requirement. That is another challenge.
Ma'am, PPT is not visible.
It is not visible, sir.
Ah, yes. Just
No,
click.
I'm still in that power of quantum computing slide.
But it's not. Can you share again?
Sure,
Participants
sir.
are also
Sure.
not visible. Yeah, sure.
Okay. Is it okay now, sir?
Yes, yes.
Okay. Okay.
Yes.
Yeah. Yeah. So I hope this is the same slide. I have not changed any slide from this. So again, manipulating a quantum state is another very big challenge. These are all the constraints that we have to work. Okay. So the next one is the next one is what are all the quantum mechanical postulates that we want to check. So again, what was the motivation where we actually left? So we left in a point. I can give a 1 minute break, or if you want me to continue, I can also do that. That depends on you, sir. If they want a 1 minute or 2 minute break, I can do that. Otherwise, I can directly continue. Okay. Ah, what is the demand? Let me check. Continue. Okay, sure. Thank you. Thank you, sir. Thank you, ma'am. Okay. Okay. So the challenge is, now you know that what you can do and what why you need it. Now the thing is how you can actually realize all these powers of quantum. For that you need to know a few very principles. So these are like the rule books. Okay. What you should be remembering. First one is the superposition. Superposition is a very like a quantum, not a computing phenomena, it's a quantum mechanical phenomena only, where we believe that two like multiple quantum states can exist together simultaneously. All the mathematics we will be looking into the details of them maybe tomorrow. I probably will be using a pen tab tomorrow for you for better understanding of yours. But just today, at least understand the basics. That superposition is the power that of a quantum mechanical system that allows a quantum state to be in multiple states simultaneously. What do I mean by that? That means, say, 0 and a 1, a finger story. So, finger down is state 0, finger up is state 1 or state 1. Now, I can say my finger itself is a quantum state. Why? Because my finger can exist in both finger down state as well as finger up state. Okay, that is superposition. Now if I increase, say if I give you two fingers for example, then how many such information I can actually encode? Finger down, that is 0 0, plus finger 0, finger down, finger up, that is 0 1, plus finger up, finger down, that is 1 0, plus finger up, like both the fingers are up, 1 1. Likewise, you can see that only with two fingers or two qubits I can store four input or four quantum basic quantum states, right? Anywhere we can exist, our two fingers can exist in any state, but our two fingers exist in a superposition of possibilities. So our four, that 00011011, are our four possibilities that a quantum state can exist into. Similarly, if there is 3 qubits, it will be 000, 001, 010, 011, 100 till 111. So there will be 8 different possibilities of that, right? That is superposition. Entanglement is a quantum mechanical phenomena where we believe that two or more objects they are somehow either correlated or anti-correlated with each other. What do I mean? Say, uh, say the movie Judwa. It's very easy for me to illustrate. That's why I use this example. That Salman Khan movie Judwa. If you have any one of you have watched it or not, I don't know. But if you watch it, you will see like so both of them are like Judwa of each other. They look exactly similar with only a few properties they differ. But if you actually hit one Salman, you will see on the other hand, it's kind of a telepathic thing where on the other hand, that other Salman will also fall in the ground. So these stupid concept that they actually used, which is never feasible. I don't think if it is ever feasible or not. It's only feasible in quantum level. Of course, I don't think that Salmans exist in the quantum level. So this kind of concept was entanglement, where whatever you do, whatever operation you do on one particular qubit, if that particular qubit is entangled or somehow correlated or anti-correlated with another qubit, now there is no like such matter that how much, no matter how much separated they are, they will behave some sort of like magical behavior. They will behave either similarly or exactly dissimilarly depending on their correlation equation. If it is like down, then it will be down as well. If it is like down, it can be up, depending on its whether it's correlation or anti-correlation, and similarly vice versa. Okay. Now there is one paradox here as well, because Einstein actually disapproved this concept. He told that it is never possible. So, but then what he does is he check that how can something be faster that light of the speed. So, how practical this quantum entanglement is? You might be asking these questions, but the answer is definitely you are right. It is not really that much of practical, and but there is certain constraints that you have to follow. Like there are quantum repeaters, there are a lot of other like challenges or specifications of the quantum physical system around you, which will actually check for the entanglement between these two qubits. So there are a lot of other stuffs, but the thing is that even the this particular theory obeys the uh, theory of relativity of light, that in with respect to the speed of light, assuming that nothing can go beyond that, it actually quantum entanglement exists, and Einstein called this particular phenomena as EPR paradox, and he called it as a spooky action at a distance. But later life, he also approved this theory and he called that okay, this exists. We actually are not going beyond light or speed of light. We are not going beyond the speed of light, but this exists. But definitely there are a lot of physical constraints associated with that as well. Okay. So this is the second phenomena. So superposition, the first one, entanglement is the second one. So is the cat live or dead? That was a very famous Schrodinger cat equation and cat experiment. There is a box and there is a cat within the box. Now, unless you open the box, how can you tell that whether the cat is alive or it is dead? You cannot tell that, right? So, exactly the same thing you can equivalently compare with the concept of superposition, that your box exists in two possibilities simultaneously. One is your cat being alive, second is your cat being dead. So, that flavor or that provision of letting one state exist with multiple possibilities, that provision is called superposition. I hope I'm clear now, right? So mathematically this is the thing. Forget about the symbols that you can see at bottom, like that vertical bar and the angular bracket. Forget about that, I'll be talking about this tomorrow. So you can assume that within a black box there is some ball outside the box which is k0 or c0, and something which is within the box which is 1. And superposition is where we believe that the ball can be, there are no two balls here. Okay, we are just assuming that the ball can either be outside or it can be inside. So that's why it's a 0 plus 1, right? Okay. Similarly, entanglement, where we believe that are their direction same. There is something like this is anti-correlation. So say if I measure something here and I get a 0, then based on my measurement and depending on the correlation that I have used, I can, without any measurement, I can directly guess that okay, that means that the other qubit at the other end has to be either 0 or 1, because I know that what is my measurement here at one end. So that criteria or condition is called entanglement. Okay. And definitely there is a concept of maximally entangled pair, which is also called Bell's pair, where we believe that 0, 0 and 1, 1, they are actually maximally entangled with respect to two qubits. And also it is the like other factor wise also, if it is like three qubits like 0, 0, 0 and 1, 1, 1, then also there is a lack of kind of coupling, there is a coupling error, or that chance gets more than whatever you can get for 0, 0 and 1, 1 only. That is for the 2 qubit. So for 2 qubit, you can actually realize the maximum power of the entanglement, and that is called maximally entangled pair. So 0, 0 minus 1, 1, it is also maximally entangled, and 0, 1 minus 1, 0, and 0, 1 plus 1, 0. All these four are called Bell states. BE Bell states. Okay, all of them are called entangled states where we believe they are in the maximum entangled status. Okay, next is the quantum bit or qubit. Since you know linear algebra, I've seen that as per your syllabus. So tomorrow I will be starting with directly the mathematics of these. So kindly focus today on the theory part so that you can understand it better. So Ket 0 and Ket 1, this is called, and the you just see the picture where we believe that this is a ground state, the first line. This is a nucleus and the excited state, and on the application of some light it will actually go from the ground to the excited state. But though some possibility or some probability, if they exist in both the ground and the excited state, we call that one as a superposition. And this particular thing is known as a quantum bit or qubit. Okay. So anything that obeys the quantum mechanical postulates or that actually obeys the quantum physics principles, we call it as a quantum particle. Okay. Exactly the same picture, you can see that one. There is a small error here, I guess. Yes. So alpha 1 and alpha 2 are complex numbers where alpha 1 it will be a square. The square terms are missing. Okay. Just put it, just note it somewhere. It will be alpha 1 square plus alpha 2 square equals to 1. So this is 0, this is 1, and this is 0 and 1 both. So just see here, it is these two circles, they represent bits or classical bits, and the third one represent quantum bits or qubits. Where the orange and the blue color, you can actually see them merged together, and they actually represent some quantum state, which is alpha Ket 0 and beta Ket 1. Similarly, this is something for the entanglement. And then the Dirac notation, the- just as I have said that this notation basically, this one say, yes, so this one, whatever you can see, the straight line and the angular bracket, the straight line and the angular bracket, they actually are part of, they are one of the Dirac notations, which is called the Kate notation. Another one is the Bra notation, and together they are called as bracket notation or Dirac notation. Both of them are same thing, and this was discovered by Dirac, scientist Dirac. So, according to his name, it is called like Dirac notation or the bracket notation, right? And there is a concept of inner product and outer product and all this stuff based on these things. So this is a representation of what we want with it or how we want to manipulate a quantum state. If it is a bra notation, that means it is a row vector representation. If it is a click notation, it means a column vector representation. Accordingly, we will manipulate the quantum states. Right? Okay. Similarly, you can see one. So AB belongs to the complex vector space C cross C. Ket notation, Ket is like this, that a vertical bar and followed by a symbol followed by a angular brace. And this is Ket is basically the representation of a column vector. So it's A1, A2. Similarly, the bra, which is a this thing, a row vector representation, which is B1, B2 in the column form, complex conjugate of that. So complex conjugate or conjugate of a row vector is equals to a column vector, and vice versa. Complex conjugate of a column vector is basically a row vector. So that's why you can see B1 star into B2, B1 star and B2 star. Where B1 star is the complex conjugate of B1 and B2 star is the complex conjugate of B2. What do I mean by that? Say 5. Okay, let me ask you. Let me ask you. What will be the complex conjugate of 5? What will be the complex conjugate of 5? Yes, it's not minus 5. 3, it's only 5. And what is the complex conjugate of, say, 2 plus 3i? What will be the complex conjugate of 2 plus 3i? Yes, 2 minus 3i. Absolutely. Thank you, thank you. Exactly same. So exactly the same thing I am trying to say. So if it is only 5, it will be 5. So that means a column vector 5 3 will be 5 3. If it is column vector 5 and say 2 plus 3i, so it will be 5 and 2 minus 3i in the row vector form. Okay. And the bracket one, this is the bracket notation where it is like bra b into kate a, that is b1 star b2 star into a1 b1 in this form. Just you multiply them, it's a 2 cross 1 matrix, and this is a sorry, this is a 1 cross 2 and this is a 2 cross 1. So the product will be a 1 cross 1. That means a single value, so it's b1 star a1 plus b2 star a2, that is a single value. Similarly, if it is ket bra, that means first it is ket A and then it is bra B, then it will be first the column vector A1 into B1 B2 in the row vector form, and it is a 2 cross 1, it is 1 cross 2, so the product will be a 2 cross 2 vector, right? So it is A1 B1 star, A1 B2 star, A2 B1 star, and A2 B2 star. So it's a ket bra is a 2 cross 2 form, and bracket is the single like variable form. Okay. Similarly, you can see like ket 0, this is a ket 0 and this is 1 0, and ket 1 is 0 1. How we have got this one? These are the assumptions. We assume that ket 0 is represented by 1 0, and accordingly all the like theory whatever we have derived based on that, where the top one represent that it is ket 0 not ket 1, that is this one represents, sorry, this one represents that it is high for 0, and the lower 0 represent it is low for 1. Don't get confused. Okay, so the top 1 represent it is high for 0, low 0 represent it is low for 1. Similarly, for ket 1 equals to 0 1 in the column vector form, the top 0 represent it is low for 0 and high 1 on, actually bottom represent it is 1 for 1, that is it is high for 1 likewise. So they are orthogonal. What is orthogonal? That is you just take the bracket notation of them, check whether it is 0 or not. If they are 0, it is orthogonal. So we'll just check it here. So it's bra 0, which is 1 0, into ket 1, which is 0 1 in the column vector form. So it's 1 into 0 plus 0 into 1 equals to 0. That means ket 0 and ket 1, they are orthogonal to each other, right? And what is normalization? Just check that ket psi is equals to ket 0 plus ket 1. Just add them up, and what you are getting is 1 1. So ket psi, I just what I want to check, I want to check that whether ket psi plus psi, this is normalized or not. So for that I have taken the same thing, ket psi, which is equals to ket 0 plus ket 1. Why? Because we are taking a superposed quantum state as ket psi, ket 0 and ket 1, and alpha beta or alpha 1 alpha 2 we are ignoring here. So it is 1 0 plus 0 1, that is 1 1. Now bra psi ket psi, that product is equals to, if you multiply them, that is equals to 2. That means that ket psi is not normalized. If it is normalized, then the value should be exactly equals to 1. Then this is the second thing, which is a block sphere. It is also very important. Or kind of a, you can see there is no physical existence of this thing, but this is a diagrammatic representation of multiple quantum states in the quantum space, or the we call it a Hilbert space. Again, I am assuming that you have a bit of understanding of the Hilbert space, orthogonal, orthonormal, all these stuffs. Okay. inner product, outer product, all these things. So this is a diagrammatic representation of the quantum states, where if you see, we actually have represented, see, three states. The first one is the Ket 0, which is a pure state. Just check where is Ket 0, this one, here. Then we have represented Ket 1, which is here. Of course, there are certain probabilistic amplitude or say amplitude that we have multiplied with, Ket 0 we have multiplied alpha, Ket 1 we have multiplied beta, and these two are basic quantum states. But there is another one which is Ket psi, this one. So this is also another one quantum state that you can represent in the block sphere, right? And there are certain constraints that you have to take into mind, where there are two angles you can see there, like theta and psi, or theta and phi, where a generic quantum state in block sphere, in a three-dimensional block sphere, a generic quantum state can be represented as ket psi is equals to alpha ket 0 plus beta ket 1. With several substitution and a bit of mathematics, you can check that alpha is basically cos theta by 2 into ket 0 plus e to the power I phi sin theta by 2 into ket 1. Where, of course, if I change the values of theta and psi, I can actually depict or say project different quantum states. For example, if I choose say theta equals to 0, so what will be the value? It will be cos 0. What is the value of cos 0? So it is basically 1. So it's 1 into ket 0 plus e to the power I into phi into sine 0 by 2, which is 0. So sine 0 is 0. So the entire term will be 0. So ultimately we'll come up with the ket 0. So that means if theta is equals to say A, B, C, whatever it is, depending on that, the quantum state representation will also vary. Okay. Same thing, you can see it over here, the same exact thing, where theta we have chosen as 0. So it's cos 0 by 2, ket 0 plus e to the power I phi sin 0 by 2 sin ket 1, where the entirely the second part will be actually removed and we'll be getting only the ket 0. Similarly, for theta equals to pi and phi equal to 0, there will be another equation, right? Okay. Okay, now the next thing is, so far what we have learned. Uh, let me pause here for 1 minute. Let me ask you if you have any question. We can actually cover that. After that, I will again start. So, anyone has any question? If you want, you can ask me, or just let me know if it is all good. If it is you have don't have any question, then I will proceed. I got one reply. Anyone else? All good. Photon is discrete, but we are taking with continuous. Fine, ma'am. Okay. I just got a one question. No, Prasad, I guess. Yes. Now we are assuming the wave property of light, sir. What we are assuming is that instead of the discrete property of light, which is the particle form, we are assuming because of the de Broglie's. I actually have not got that opportunity to get into the physics part with all of you, but we actually have seen that there are a lot of experimental proofs for that as well, where we have seen that there are wave particle duality of light by de Broglie's hypothesis. So there, because it is wave, we believe that it is a continuous some sort of quanta that is there. So with the probability, so you can assume it in this way. Say because quantum is very much similar to our human brain, that's why we connect it with DNA computing. So you can think it like that. Say right now I'm assuming कि आज शाम को I'll be having some chana masala, and I'll be taking my kids to say doctor's home because he's having some fever, and I will also be doing some, if possible, I'll be watching a movie. Likewise, say for example, don't consider it very seriously, just some examples I'm taking. So that means, but whenever, say for example, if you ask me that, okay, right now, what you're thinking, Nivedita, I'll be telling you the answer that, okay, I'm planning to have chana tonight. So I'll be giving you one exact answer. So that is discrete. But the way or inherently how I'm thinking is I'm actually processing three different thoughts simultaneously. That is because my brain is able to process non-deterministically, where from one point I don't know where exactly I'm going to head towards, but I will be thinking all these three solutions. So until and unless you ask me, it's 33.33% probability of all. I can either do this, or I can do this, or I can do that. So there are all three possibilities together. But whenever you ask me a particular question, just like a particular say measurement, I'll be giving you exactly one answer. So similarly here also, we are considering because we want to explore the power or the exponential power of quantum computing. That is why from the wave nature we have actually, the particle nature, we actually have tried exploring or started exploring the wave nature of it. Where we believe that everything exists in form of some probabilities. It's
P-
33% probable to have
people,
chana, 33% probable to take my kid to doctor's home, 33% probability I also have to take or say to watch a movie, and 1% probability is there that I'll not be doing anything. I'll be just be listening to some good music and will be sleeping. So likewise,
ma'am,
similarly
please
here
share
also,
the screen. I think screen is not shared.
am I audible? Is there any
Yeah,
issue?
yes, ma'am. You're audible. The screen is not shared.
I'm not sharing, sir. Yes.
Okay, okay. Yeah. Go ahead.
Yes,
Please
I'm
go ahead.
not sharing right now. So, but I'm just answering their questions, trying to answer their questions. Yes. So, it is just that we are exploring the wave nature of light through probability. Okay, there was one more question. Let me check. Please explain what is the meaning of high on zero or five. I will be. I got your point. Maybe you are new to it, that's why. So Kate 0 is basically represented as 1 0 in a column vector form. Today I'm not getting into the mathematics. Tomorrow it will be super clear to all of you. I can assure you that. So it is just that Kate 0, that 0 is a kind of an index. So Kate 0 is an index of 0. You can assume in that way. Where 1 0, like 1 on top and 0 on bottom, represent that 1 on top represent that it is high for 0. Because the 0th index we are working on. So Kate 0 is basically 1 0 as a column vector form. And 0 on bottom represent that it is low for 1 because we are talking about the 0th index. It will be very clear as and when we proceed. Okay. PPT, PPT. I'm not showing the PPT. I just will be sharing it right now. Okay, I hope it is clear. Anyone, I think everyone's doubt so far has been just shared. Okay, I think the same thing. Okay, great. Yes, so again, we are getting back to the PPT. So right now we have seen superposition, entanglement, and a basic of qubits, block sphere, all those basic things we have seen. Right now, there is another very important concept here, which is this one, the quantum no cloning theorem, which is extremely important for in context of cryptography as well as communication. So the mathematics, I will not go into much of it today, but the concept is very easy. So quantum no cloning theorem means An arbitrary quantum state. An arbitrary quantum state where you do not have the preparation contextuality means, in easy words, you don't know exactly how they have prepared the quantum state. It is an arbitrary one. So you do not have the much of the knowledge about the angle, the momentum, whatever it is, because ultimately it's just a photon, right? It's no like hard particle that you have access about. You can tune it, control it, anything you want to do, you can do with that. It's not like that. Ultimately, it's a photon or some other very strong quantum, say, physical hardware devices. But the thing is that if it is a quantum device, then if it is an arbitrary quantum state that you have encoded within that quantum hardware, you can never clone that same quantum state ever in your life. Cannot do that. What is the advantage? Say, say for example, Ramesh had sent some data to Gargi. Okay, Ramesh and Gargi, both of them are communicating. So Ramesh has sent some data to Gargi and say a love letter. That will be very easy for you to remember. And Gargi has us, okay, so Gargi has received it and just okay, ऐसा कुछ था कि okay, if you have just put your phone number or put your say some fingerprint so that whenever it will come back to me, I will actually understand or acknowledge that okay, it was actually you and you accepted my love. Kind of that. Just imagine. But say instead of Gargi, some envy or say some enemy of Gargi, say Survi, has received that letter. So if she tries to do anything with the letter, for example, say the letter got distorted. Okay? So whenever that distorted letter from Survi again gets received by what was the name? Say, I don't know. Okay, say Rahul or whoever it is, say Rahul. Then Rahul will instantly understand that okay, maybe my communication or my attempt to communicate is lost. I have to again reinitiate another communication or say another attempt I have to reinitiate to communicate with Gargi. But at least it is guaranteed that someone in between me and Gargi is trying to tamper with my data. Similarly, for quantum, it is the same thing. If Alice and Bob, which is a conventional names for the sender and receiver for cryptography, so if they send or want to send some data from sender send to receiver send, if any eve or eavesdropper accidentally or purposely gains the access of the data, and if they try to tamper by any means, by two means, what are the two means? Either he will make the data unavailable or like he will take the data and try to clone it back so that he or she can remain in disguise. But if this is being tried, then if it is a quantum state or a quantum love letter being transferred from A to B or Alice to Bob, then it will be very easily kind of monitored or it can be captured, right? So that is the power of no cloning theory. It cannot really clone any arbitrary quantum state. So the equation here is very simple that you have a blank state. Consider the example of a say Xerox machine where you actually give what you give in a Xerox machine. Say you actually go with a one paper, say your higher secondary mark sheet, you want to print it. So what you do? You go to the machine with your paper, that is the state size that I'm talking about, and there is a blank state which is the blank paper in the printer or the Xerox machine that the guy will be putting the blank paper. What will be the output? Your original sheet will come out definitely, and in the blank paper, your HS mark sheet will actually be printed and that will also come out. So if nothing is wrong, then this should be the state of the quantum system under no cloning. Sorry, under cloning. But if it is not true, if it is not true, or if we say like there is only one state say psi, so every time if it is only psi, that is the state is known to me. it is not arbitrary, then maybe I will be able to clone it. Otherwise, if I do not have any much knowledge about the state, it cannot be copied or cloned. Okay? The same thing is called quantum no clone theorem. Similarly, quantum teleportation also. You know the meaning of teleportation, where we believe that basically kind of I'm not be telling anything and that will be by this means or that, it will ultimately be communicated at your end. So that kind of that idea of telepathy. So it is also very much similar where we believe that a quantum state, without sending that quantum state, we can recreate it. Remember, we can recreate the quantum state from sender to receiver by just sending some very basic classical bits. So definitely I'll be having some setup at sender and receiver, but after that, with a very minimal manipulation or mathematics, we can actually ensure that that message is sent from the sender to the receiver without actually sending the data. And this theory is called quantum teleportation. Okay, this is very big concepts like teleportation, cloning. Understanding the full-fledged maths is very difficult. So maybe we will be doing it not today. Definitely, you might be having like having questions in your mind that how practical it is, how to do that, all those stuffs. We will be going through that. Now again, now there is I guess two more I want to talk about just after this one. That is teleportation is over, so we want to talk about the interference as well as decoherence and measurement. So in a very nutshell, just a two or three lines I'll be talking. So understand it just. So interference is a concept, quantum interference, where we have talked about that it can actually exist in waves. Now, whenever it is wave, if they somehow merge with each other, two waves, so it will be a big wave, and if don't, they will be a small wave. Very easy example. So for quantum context, while we are actually doing some manipulation with some quantum states, the concept is, say, I've told you that okay, I initially had three possibilities. Either I can have an external, or I can go for my doctor's home for my kid, or I can watch a movie. Say I will be telling you that okay, but I think that there is rain outside, so you cannot actually go for watching the movie outside. So in that case, or that what does it mean? That means I cannot really go with my kid to the doctor's home, as well as I will not be allowed to take my kid to sorry, not be allowed to go for watching a movie. So that means right now I am left with only two options. What's the one option? That is cooking good food or having exam, right? So these kind of actually like shrinking possibilities. These kind of feature or phenomena in quantum, they are called destructive interference. This is also interference, but this is very destructive because the waves actually are cancelling out each other. But otherwise, otherwise, if I say that right now I have this possibility, but if there is no rain, then definitely I will opt for watching a movie, or opt for watching a movie at hall, some cinema hall. Or I say, I am telling that okay, definitely then I will be going to a movie, to going to a shopping mall to buy some clothes. So that means at any time I can actually increase my possibilities as well as decrease my possibilities or chances. Whenever I increase it, we call it a destructive interference. Whenever we decrease it, we call it an sorry. Whenever we increase it, we call it a constructive interference. Right? So this is interference. Now the second one is measurement. As just I have said that measurement is very peculiar and you have to do a lot of manipulation with measurement because you do not know that out of all those 32 states of that pencil example, you don't know that after say 3 or 4 times what exact output you are going to get. So you don't have any access of that. So what output you are going to get, that is very very random and you don't have any access to that, right? So that is the theory of measurement. So in order to get your desired output, what you should be doing, you have to actually manipulate the states or manipulate your computation in a way that you get your desired results and not the gibberish other results which you do not want to see. Okay. And another one, as I've said, another one is the decoherence of the enemy. So decoherence is some enemy of quantum computation. Decoherence is something like you have power right now, you don't have power after 5 minutes. So I will decover all the energy that you have. Okay, so that is decoherence. Now next is classical versus quantum logic. So right now let us again go back to the classical discussion that we were doing, that in classical logic gates or classical gates or our basic TTL logic, transistor logic or diode, all those stuff. There we have seen one thing, that is what were the basic gates like AND gate, OR gate, NOT gate, XOR or exclusive NOT, and yes, and NAND and NOT to universal gates. So all these gates we have seen. Now the thing is, all of them or most of them are based on irreversible logic of computation. What do I mean by that? Means, say I have given you an AND gate, a truth table of an AND gate, right? Where instead of four, I just have given you three pairs, 00, 10, and 01. Now, if you multiply them or if you do AND, what will happen? What output will be getting? We will be getting either 0 or 1 or sorry, we'll be getting 0 for 00, we'll be getting 0 for 01 as well as we'll be getting 0 for 10 as well. That is, you don't have any provision to get a 1. Similarly, if you are given with a 0 or no, sorry, OR gate, and I have given you all the four options like 00, 10, 01, and 11. Then in three cases, for 01, for 10, and for 11, you have what you have got? You have got a 0. Sorry, very sorry, you have got a 1. So that means put 1, you don't have any provision to get back to the original input from where you started. So if I gave you 1 for OR gate, can you exactly tell me that what was the input, whether it was 01, 10, or 11? You cannot do that. Similarly, if I give a 0 and tell you that you got me a 0 and ask you that what is the input, you cannot give me that because it can be either 00 or it can be 01 or it can be 10. Okay, so this particular theory is called reversibility versus irreversibility, and quantum computers are mostly they are based on this irreversible logic of they are built on the reversible logic of computation, whereas all the classical computers mostly they are built on the irreversible logic gates and its computation. Okay, so There is only one classical gate that you can directly use for quantum purpose or for quantum gates. Can you name what is the gate? Can you tell what is the name of the gate that is there in classical, but it is also used for quantum as well? Yes. So if you have answered Hadamard, Hadamard, have you ever seen Hadamard gate in your classical Boolean algebra? So it's not Hadamard. Yes, yes. So the answer is not gate. It's not Hadamard. Where you have seen Hadamard gate? So it's only the not gate. Okay, there is someone is telling that there is an issue with my voice or background noise. Is it okay? Are you able to hear? Okay, for those, because I'm already having very like a issue with my voice because of fever and all. So I'm trying to be loud at as loud as possible. Uh, okay, okay. Let me just switch off my fan. Oh, no issue. I'm just trying. Just give me a minute. Just trying to switch off my fan. Okay. So meanwhile, let me continue with the discussion. That is, there is an issue. Sorry, there is something called an irreversibility and reversibility, where we believe, I hope it is now bit clear, more clear, and the noise is less. So where we believe that the classical gates are irreversible in nature and the quantum gate is reversible in nature. Now you will ask me that what is the advantage of a quantum gate being reversible? The logic is, any reversible operation, anything that actually preserves the energy and the dissipated heat. Okay, and heat is nothing but that information that you want to protect or that you want to store. So any irreversible logic, just like the your basic AND gate or gate, except the not one, because zero gives you one and one gives you zero. So from output you can actually very easily say what is the input or what were the inputs. But otherwise, all these other gates like AND or XOR, exclusive NOR, all these gates, NAND, NOR, all of them, they actually lose some sort of information or heat in between the input to output translation. That is why in quantum we only rely on the unitary operators, and if you check any quantum circuit, you will see that after our oracle, or we will talk about that what is an oracle and all, but after a particular operation we always try to undo the quantum state. We we actually reverse it back by using the same gates, same set of gates. So remember, just remember, all quantum gates that we use, they are basically your reversible gates. All the quantum gates are reversible, right? Okay. And here you can see that gates without superposition, a few gates are there, like the uh, NOT gate. You can see it over here. So it's kind of an inverter. So Ket 0 will be 1001 and Ket 1 will be 01. Like Ket 0 will be 10, and from 10 it will be 01. That is Ket 1, and Ket 1 will be 01, and it will be actually 10. Okay, and n equals to 0110. This is that particular quantum gate that you can use on like before the any of your quantum state in order to work. For example, if 0110, that quantum gate works on gate 0, which is or say gate 1, which is 01, You will see 0 into 0 plus 1 into 1, that is 1 on top, and 1 into 0 plus 0 into 1, that is 0 on bottom. So that n equals to whatever you can see here, 0 1 1 0. This is the inverter gate or not gate, or also a quantum gate, the very basic quantum gate, which is exactly same as one of the classical gates. So that will make your 0 1, which is gate 1 to 1 0. So n on 1 will make it gate 0, right? And this is a single qubit gate. These are all the single qubit gates like Z. And also, just to tell you, this NOT gate or inverter has also another name. So that is called Pauli XZ. So it's a Z is equals to 100 minus 1. How we have got it? All of these gates like Z, S, T, whatever you can see, they all come from a very generic symbol, which is 100 e to the power I theta. Okay, that is the matrix. Now if you put the value of theta is equals to say pi, then it will be to the power I pi. Just expand it, right? What will be the expansion of e to the power I pi? Anyone? Anyone can say what will be the expansion of e to the power I pi? Is it still a lot of noise? PPT gone. I actually no, I'm not sharing. I just asked a question. I just asked a question. Yes, yes. Okay. A few questions, a few option answers I got. Cos pi plus I sin pi. Yeah, but it should not be noisy. I actually switched off the fan as well as AC. Yeah. Okay. Thank you, Kiran. Thank you for confirming. Yeah. Yes, absolutely. So e to the power I pi is, let me again go back. So e to the power I pi is nothing but cos pi plus I sin pi, or e to the power I theta is basically cos theta plus I sin theta. Now, if you put the value of pi in place of theta, you will be getting cos pi plus I sin pi, where I sin pi is basically 0, and cos pi is basically cos 180 minus 0 degree. Likewise, the quadrant map, just do that, it will be minus 1. So that is why you got 100 minus 1, because cos pi is minus 1. Similarly for S, 100 I. For particular values of theta, you will be actually getting different gates. And in Qiskit, we'll be actually getting or maybe all these derived gates. You might be getting T, Z, As, likewise. All of them are same with only the theta being different. You might ask then why it's being like, why they are trying to confuse us, why can't we code it and get it directly? Because otherwise we have to remember. The case is because a few gates, because of the Fourier transformation and a few of the applications are so much in use. That is why only they have just put them separately so that it's handy, nothing else. The basic concept is same. All of them are rotation gates. Phase gate is also a part of the rotation gates. Pauli XYZ, all of these gates are part of that. Okay. And only the one gate that you can see here is Hadamard, which is H is equals to 1 over root 2, 1 minus 1, right? And this idea, the Hadamard operation, this was a groundbreaking theory because the superposition, the entire concept of parallelism, quantum parallelism, exponential speed up, all those things are basically backed up, or say primarily backed up by like 70% this particular gate. This approves, only this gate allows for superposition, only one gate, which is a single qubit gate. Okay, so that is 1 1 1 minus 1. Now if you say, that means, and what it does basically, if you give a cat 0 on Hadamard, like Hadamard of cat 0, it will make it cat 0 plus cat 1. If you give Hadamard of cat 1, Hadamard of cat 1 means this matrix 1 1 1 minus 1 with a 1 over root 2, keeping considering that one aside. So 1 1 1 minus 1 on 1 0 is going to give you 1 1 on a column vector form. Again, keeping the index theory same, 1 1 on a column vector means it is basically high for both 0 as well as for 1. So that is ket 0 was a pure quantum state. Right now you are deriving a mixed state or a superposed state using the help of a Hadamard gate. Now, this is for a single qubit. Definitely, Kedziv is a single qubit gate or one finger only. Now, if I make it three fingers, that is three qubits. How you can get all eight quantum gates? How you can do that? By actually employing three Hadamard gates. So your for every finger will be accompanied by a single Hadamard gate, right? So your 0 will now become 0 plus 1, your next 0 will become 0 plus 1, your third 0 will become 0 plus 1. So it's 0 plus 1 tensor product 0 plus 1 tensor product 0 plus 1 within brackets say. So three brackets are there in between two tensor products. Now if you just multiply them very simply, it will be 000 plus 001 plus 010 plus 011 plus 100 plus 101 plus 110 plus 111. So all these eight states will be getting. So how many passive states are there? Eight. How we are getting it? By employing three Hadamard. Where you are employing the three Hadamards? On three different qubits. What were the qubits initialized with? Ket 0. All of them are initialized with Ket 0. So at the end, at the output, how many superposed states you are getting? The answer is 8 or 1. It is 1. Whenever it is superposed, it is only one quantum state. My all fingers, if they are in superposition, they will all be together and that will be one hand. Similarly, one superposed quantum state. But it comprises of how many states? It comprises of eight different basic or pure states. Okay. Okay. Similarly, a few gets like if I ask you like please just do a equality check like x is equals to Hadamard, then z then Hadamard. Just check whether you are getting the same matrix as x Pauli x or not. Similarly, I y can be zx and vice versa. There likewise a circuit equivalence definitely can be asked. That's up to you. That's just playing with the maths and linear algebra, nothing else. Okay. Then it is the C not gate. It again this one is the now just like Hadamard is the very fundamental or essence of superposition.
Uh, Nivedita ma'am,
Yes, yes, sir.
without anything on the screen, they are not able to follow.
No, I'm showing the
Maybe
screen. I'm showing the screen.
no
Oh,
screen is not visible, ma'am.
oh, just a minute, sir.
Yeah, actually, initially I thought you are not, but then when you started again,
No, no, no. I,
advantage.
I was using screen. Sorry.
Okay, okay.
Maybe.
Then it was not for a long time. It was not shown. Yeah.
Okay, okay, okay. I'm again showing it. Just a minute. Yes. Oh.
Yeah, maybe you can just repeat a few
I,
slides
I, I,
before.
I am just showing them the slides. They will understand. So, yes. So this one, I think all of you have followed, like the NOT gate that we talked about. We started with the quantum gate. Post the like cos pi and I sin pi. Post that we started with this thing, and then the NOT gate. We talked about it, followed by a few of the single qubit gates like S, Z, T, which is nothing but all of them are rotation gates. The basic one is 100 e to the power I theta, right? Where you if you keep on changing the value of theta, you will be getting different gates. And Hadamard, I just talked about this is the very basic one, 1 1 1 and minus 1. And definitely by doing the tensor product of this Hadamard, you can actually have the 4 cross 4 Hadamard, 8 cross 8, 16 cross 16, depending on your requirement. Otherwise, you can also put it in or understand it in this way, that if you have 3 fingers, you can employ 3 2-qubit Hadamard gates, just like this one, 1 1 1 minus 1. And if you do that and do the tensor product, then also you are going to get the 0 0 0 plus 1 1 1, 0 0 0 0 0 1 0 1 0. Likewise, all the 8 states you are going to get. Post that, I talked about that. Okay, so initially, how many quantum gates were there? There were 3 quantum gates. They were Hadamard, 3 Hadamard gates. How many qubits? 3 qubits. How many quantum system? Only one quantum system that has 3 qubits. So how many quantum states at input? As input, it was 3 quantum states which were basis states, 0 0 0. How many states we are getting as output? We are getting exactly one big superposed state or a mixed state comprising of all these 8 bases or pure states. Only this much I discussed. Okay. And Hadamard is the essence of superposition, right? Then I have said that there can be a lot of like circuit equivalences. You can check that x equals to, or Pauli x equals to Hadamard Z Hadamard or not. You can check that Z is the phase gate. Likewise, you can check. And then I just have like started talking about C naught gate. I hope right now it's visible, sir. It is visible, right?
Yes, yes, yes.
Okay, okay. So C naught gate is another very fundamental gate which we will be like having everywhere in computing and communication, which is the control not gate. So C naught is another one which is the essence of entanglement. So Hadamard followed by C naught. This particular pair is something that we are going to see in quantum entanglement or Bell state or maximally entangled pair, whatever we have discussed. So C naught gate is basically, you can see the truth table of it, 1000010000010010. If you just check in the 4 cross 4 matrix, only the 2 cross 2, right, like in the diagonal, if you do something like that, then just the 0110 on bottom, rightmost bottom, that is a not gate, nothing else. So basically, in very easy words, C naught is a 2-qubit gate. What are the information that you should be remembering? C naught is a 2-qubit gate. Why it is controlled means it's a NOT gate but with a control on that. And what do I mean by that? It means that there is a control, there is a target. These two are the inputs. So it's a two input to output gate where control decides the fate of the target. So in output also control will be as it is, just like whatever it was there in the input. But target will be flipped or changed based on the control target relation in the input. Again, in very easy words, if control is 0, target is 0, we will not do anything. It is 0 0. If control is 0, target is 1, then also we are not going to do anything because control hailing, it's 0. So it will be 0 1. But if control is 1 and target is 0, then output will be 1 1. That is, control will remain 1, but target will be flipped to 1 because my control was 1. Similarly, for 1 1 as well. If control is 1 and target is 1, then it will become 1 and 0. Because since control is 1, now my target will be flipped from 1 to 0. That is why you can here see only a change in the 0 1 1 0, because it's ultimately the columns represent 0 0 0 1 1 0 and 1 1. So for 1 0 it will be mapped to 1 1 and 1 1 will be mapped to 1 0. But 0 0 will remain as 0 0 and 0 1 will also remain as 0 1. That is why you are getting here In the diagonal position for 0001, you are getting exactly 1 1. There is no flip, there is no abnormality. Only for 1 1 it will be 1 0, and for 1 0 it will be 1 1. And this is the circuit form. You can see both are same, like control and target. So there is a filled circle, and the filled circle in the quantum circuit represents a control logic. It means that it is a C naught or a control naught, a lot of those things, where the field one, that particular line represents control. Meaning here if there is a zero, we will assume accordingly further calculation with a zero. Here if we get a one, we will assume further computation with a one. Simple. And if it is one, then accordingly we will manipulate the rest of the symbols. And this is another kind of representation of a quantum circuit, and where you will be finding it if you want today also after class. It's all almost like over. So what you can do is you can just go to the IBM Qiskit platform or any quantum circuit Google Map. You can just search and you can check that at least these few gets, whatever we discussed, like Hadamard, Z, and then the X, then a few of like TS. Don't worry about it, just the angles I have told you. And then this C naught. Just check that whether this particular substructure somewhere you find in the quantum circuit, in the like in any of the quantum circuit image or not. Just check whether you can find it or not. Then it will help you to map, or it will help you to go through or understand any random quantum circuit. We have to understand also how to interpret a quantum circuit. Though in Qiskit it's like automatically drawn, but in order to understand it, in order to go for further like the algorithms and all the advanced versions, we have to understand how the circuits are drawn. And also remember very important point, because there are few gates. So I will start with this tomorrow. Just remember one thing, that is in a quantum circuit or any quantum operation is nothing but a time series operation, like it's a time diagram. Here we manipulate with respect to the time. So it is just say a state of a photon or any quantum dot or quantum particle, anything you pick up, that gets transformed in multiple forms. Its probability is being plus or minus, its amplitude is being changed, it has a different angle. Right now the basis with which I'm changing it is being different. Now this right now and all these things are with respect to each and every quantum operation. Your entire finger, or your say hand with 5 fingers, that is your entire quantum state, which itself comprises of a lot of basic states, is going to evolve. So it's a time evolution, nothing else. This is not same as the way we do proceed with the classical computation. Here we worry about a lot of other stuff, but here everything is with respect to the time. That is why whenever we undo something, we actually get back in the kind of a time traversal. We actually can go back to wherever we actually had left it. Okay, but what is the main catch? Whenever you measure it, you will be losing all the quantum property, all the superposition, and you will be getting exactly one output. Just like if you ask me that what exactly right now you're thinking, ma'am, I will be telling you that okay, I'm just planning to have some good food, maybe, or want to have some chana. It cannot be multiple outcome at during measurement. For a single measurement, it cannot be. From a single qubit, it cannot be. Okay, so measurement actually, what I mean is measurement actually collapses the quantumness. So you have to be very particular with how you want to devise or how you want to manipulate your quantum physical phenomena, or that is called what we call as computing. That is the computing, right, that we have to manipulate with the physics. And once you do that, we'll be deriving the correct answer. But it maybe for certain cases, if you cannot anyhow do anything, then you have to go for some post processing, which basically you can see in one of the algorithms like Shor's algorithm. There are a lot of things. Okay, so this I guess I can stop here. And So tomorrow exactly from this point I will be starting. So just let me know if you have any questions, or are we good for the next class or not? Yes.
Thank you. Thank you so much, ma'am. Thank you for the lecture. And yeah, uh, please try to bear. It will take some time for you to understand the notations, the thought process. So it will take some time, please. In the very so there are three foundational courses, if you understand, right? So please understand that QT-01 is Foundations of Quantum Technologies. So again, a lot of things will be repeated. So the syllabus has been designed in such a way that reinforcement is done 2-3 times. Basic quantum programming, again, a lot of things are repeated. When you go to quantum computation, which is QT-05, again, you will be taught all these in detail, right? Then by that time, all these will look like A plus B whole square, right? Now, immediately you can remember. Then at that time, get 0, get 1, all these words that are there will be very, very normal, because by that time you have listened to it 3 or 4 times. So please don't worry, please don't hurry. It takes time. Slowly as we go through, we'll understand. And yeah, because we are coming from multiple fields, or some of management faculty are there, electronics faculty are there, computer science are there, physics are there, maths are there. Most of the physics faculty may find it very easy to understand, right? So that's something which initially there is a disadvantage for others, but some people mathematics they also very easily understand, because they would have studied some of these concepts in their post graduation and also in their research, right? So for the others, it will take some time. So slowly let it sink. It is something like for us, when I was doing engineering, first year engineering mechanics was there. Very difficult it was for us. But after that, I used to teach engineering mechanics. Being a electronics faculty, electronics student, I used to teach engineering mechanics for many juniors, many of my classmates who failed. But initially, it was very difficult for me to do that, right? So it's a simple example I'm sharing, because it's a new concept. It will take some time. But if you understand, she has been studying from 2014. So after 11, 12 years, she is able to speak so much, and it will take some time. So please, I think Madam will also share her own experiences as she picked up all these concepts. So it will take some time for us to digest. So please don't worry, we are on the right track. Slowly, slowly, we'll try to take you through this course. We will, when you come to FT QT-02, which will start shortly, at that time, you will, when these things are being revised again, there is a reinforcement which is done. Some of the concepts are repeated, and at that time, you will feel, okay, okay, now we know all these, right? So please listen carefully, focus, and I think most of you are listening to the lectures very seriously, and you are focusing, and most of these things will be repeated. Please don't worry about it, right? So all these things will be discussed in detail over a period of time, right? Thank you so much, madam. We will meet tomorrow. Madam will be taking continuous lectures. So tomorrow onwards, she's actually a classroom teacher like Dr. Mustafizur. So she'll be using the slides and write the content and all equations she writes, mathematics and all. So over a period of time, we will look at. But please understand, this is the first course, and it is a course which is giving you an overview. So only briefly things are being touched upon. Briefly, very briefly. This is what, this is what, this is what, like that, right? Then in detail, everything will be taught. So till that time, please be patient, right? So I'll encourage you. So even if you don't do QT-00 and QT-01, you can follow QT-02 onwards. There is no problem. But if you do QT-00 and 01, you will be very easily following QT-02. That's what is the advantage, right? So please bear and slowly continue and learn. I wish you all the best. So we will meet tomorrow. I think tomorrow evening the exam will start. For some of you who are worried about the quiz one not being visible, it is because few faculty members have requested that because they started the exam and they could not complete, and it got closed and they did not attempt all the answers, they got less than 4 marks. For all those who got 4 and less than 4, we have given a second attempt. So for those who are rating the second attempt, the others will not be able to see their grades. So please be patient. Tomorrow by lunchtime, we will close that all the attempts. Second attempt we are giving for quiz one. Good news is we are opening quiz 1 again. At 4 o'clock, we will open quiz 1 along with quiz 2, right? So those who have missed quiz 1, please write quiz 1. And along with that, you have to write quiz 2 also. And by Monday evening, you have to complete both the quizzes. So I hope now that most of the Canvas problems are solved, most of you are able to access Canvas, most of you are logging in, most of you are attending the lectures, most of you are viewing the lectures. Some of you are following on YouTube also, I know. So all these things put together, I hope you will do a wonderful job. Thank you so much for this patient time. Please increase the time, sir. Time in the sense? Okay, the quiz time. Quiz time, 20 questions, 30 minutes is big time actually, I think, right? Otherwise, what will happen is you will use ChatGPT. That's the problem. So yeah, we'll see if it is there. Let me see. Let me discuss with other. I think I will discuss with Dr. Anil, AP State Council for Higher Education. Then I'll discuss tomorrow. Ma'am, I think there is some issue with the audio. Nivedita, ma'am,
Yes,
some
yes,
of
ma'am.
you are like that. So yeah, ma'am will make the arrangements. No problem. Don't worry. Yeah. And mostly, ma'am will use the whiteboard, so you will enjoy the lectures. You can write down the notes while that, right? So hopefully that's where.
Yes.
So madam will be teaching, and in between, Dr. Ashwath will be taking one lecture on September 1st, when madam is busy making the QT-06 lecture. And after that, Ashwath sir will come back and take lectures on quantum sensing and quantum materials, and that will be completing the course, right? So hopefully you will do well, and I wish you all the best. Thank you. Thank you, ma'am, for joining. Tomorrow at 3 o'clock, we'll continue
Thank
the
you, sir.
lecture.
Thank
Yeah.
you, sir.
Thank you.
Thank you, everyone.